So our speaker today is Dr. Peter Schultz. Okay. Pete's research focuses on the impact of cratering processes as revealed by laboratory impact experiments, the planetary surface record, and terrestrial ground truth. His laboratory research has covered a wide range of topics: atmospheric effects on ejecta placement, impactor survival, secondary impact processes, and typical shock effects, high-speed spectroscopy of impact vapor/plasma, impact angle effects, shock propagation, vaporization, target damage, and low field evolution, projectile fate after impacts, and crater scaling relations. Pretty good mouthful there, right? Of particular recent interest has addressed the origin of fluidized ejecta and blast winds around craters on Mars. Such basic research led to participation in numerous NASA planetary missions, including Magellan, Deep Impact, Stardust Next, Epoxy, and L-Cross. He cut his teeth, so to speak, on basic lunar research: floor fractured craters, beginning and end of volcanism, lunar swirl generation, polar volatile evolution, assessment of the size of impactors, evidence for ongoing lunar tectonic activity, and what caused the difference between lunar near side and far side. The last study proposed that a giant impact on the far side actually caused a concentration of mare on the near side of the moon, i.e. what we see as the man on the moon. On Earth, his research has included the discovery of 8 impacts in Argentina, documentation of a witnessed crater-forming impact in Peru in 2007, and studying the effects of a giant cometary air blast across the Atacama Desert in Chile only about 11,500 years ago. He has published more than 200 papers and authored a book called Moon Morphology. Most recently, he contributed a chapter to a new book that shares stories about growing up during the dawn of the space age, called The Space Age Generation. He received his bachelor's degree from Carleton College and PhD from the University of Texas, Austin. He subsequently went to NASA Ames as an NRC postdoc researcher, then staff scientist at LPI, and finally professor at Brown University, becoming emeritus in 2014. His students have gone to become well-respected scientists across the world. He served as the science coordinator for the NASA Ames Vertical Gun Range from 1980 to 2014, and was the principal investigator and director of both the NASA Rhode Island Space Grant Program and the Northeast Planetary Data Center at Brown. He's been awarded the Distinguished Scientist Award from the Hypervelocity Impact Society, the Barringer Medal from the Meteoritical Society, Medal of Achievement from the National Academy of Sciences in Argentina, Distinguished Alumni Achievement Award from Carleton College, and the G.K. Gilbert Award from the Geological Society of America. Dr. Schultz also has an asteroid named after him. Asteroid 6952 is named Pete Schultz. So I'd like you to give a warm Skyscrapers welcome to Dr. Peter Schultz.
Yeah, so I think last time I was here was for National Assembly, but I also was here in 2007, I believe, giving a talk about the moon and why it may not still be dead. Well, I'm following up with that talk with some new insights. Some of this is coming because of what's been learned in Thomas Sullivan. Some of it is just to sort of clear the slate to make sure that everybody knows where some of his ideas came from a long time ago and what happens when you have new missions. So what I wanted to just start off with was this beautiful picture of the moon and get into the business of what we know from Apollo. That's where we want to begin, because I'm going to go backwards in time. Apollo was so seminal, and by seminal I mean it changed our view of the moon. We thought there were places on the moon that were so active, and some places that were maybe some certain areas, other people said it was dead. So I'm going to give you this outline. It's going to be a bit of history, what's new, what happened, and then why. That's the general outline. Now, if I begin to see people falling asleep, I will fast move ahead because I know it's not going to be that interesting. No. This is what we thought the moon looked like, and the idea with the paradigm that the moon is dead. Why? Well, Apollo 11 showed It's hard to hear. Is that me or that?
That's this.
So again, over here.
No, you should be watching.
Okay.
Yeah, that's for that.
Thanks for letting me know. So Apollo 11 showed that we have the salts that were about 3.8 billion years old. This is at that nomenclature of giga annual. So if you see that, that means a billion. The other site was Apollo 12, one of the youngest sites was on 3.15 billion years old. Apollo 15 was 3.3. And then they went to Apollo 17 thinking they were going to find the youngest results on the moon. Turns out it was the oldest, around 3.75. But this was the thing. Apollo samples indicated the age of volcanism went from 3.8 to about 3.2 billion years. And in fact, we could see that there are these impact degradation models that was reflected in the way crater rays disappeared. That is the preservation of libido, or maybe even the degradation of craters. And in fact, they used this to try to estimate, to look at a picture of the moon from a space program. You could tell that a 100-meter crater might degrade to 1 degree slope within a billion years. That's an important thing to remember. Impact degradation is like rain, and it can destroy a crater, so it just gets barely visible. And I'll be exploring some of that with you. Also, there's going to be a little discussion here about interpretation of crater statistics, geophysical models, pre-Apollo debates about Gerard Kuiper, who thought it was a dead moon, and Harold Urey, who thought it was partly alive. It was a very vicious debate early on. But all of this was also at the same time when there was a controversy over Cosroff's observations that there were plumes of gas coming off the crater Alphonsus. That's where Ranger 9 went, thinking that maybe they'll find out what's there. And this is also the time when there was reactions to the idea that you're in lunar transit phenomena. Most of you know about the transit phenomena. These are these things that look like a puff over the moon, or it might be a flash. This is before we had digital imaging where we could actually record everything. Now it's been proven. Many of these impacts are what 300 impact flashes that have been reported. This is no longer fiction, it's real. There's still a debate, though, on whether or not there's anything else going on. And that's what we're going to get into today. Just so that I want to show you this example of how you can destroy a crater ray, Kepler, very bright rays. Then you get on to a crater like Copernicus, bright, but not quite as bright. And there you can't even see eratosities. And this became the foundation for giving a geological color for the moon. And I will show this again a little bit later, is the idea that you can degrade a crater down to it's barely visible. And one of the things about endogenic geophysical models was this statement. Endogenic tectonism related to the readjustment of the crust in response to the mare basalt loads during the post-Imbrian is limited to the mare, and hence is only regional in importance. This is the belief the moon is basically uninteresting. Everything stopped about 3.2 billion years ago. Don't bother me. That's it. So this is another way of looking at this dead moon paradigm. There's a lot of it's around some of these models, and this is one good example. It was based on sample ages. It was based on post-Apollo consensus in quotation mark. Consensus can be the boogeyman of scientists, because once you believe the consensus, then you tend not to do anything new. And it was explained by geophysical models as I show you here. Let me go back to this. And what this is really showing up here is the idea that you have tectonics that was under extension when the moon was expanding because it was heating up. It was forming these linear Robin rills. There was tectonic compression, which really started later after all volcanism, and then after the moon started compressing down, started shrinking. Volcanism, according to this model, it pretty well ended at around 3 billion years. There was an early period of filling, and then there was a late fill. That was the model. Well, between 1968 and 1970, a bit of personal history here. I poured over 3,000 lunar orbit photographs with magnifying glass. This is when I was doing my PhD in astronomy at the University of Texas. My minor was going to be observational cosmology. Those two don't mix well, but I did that anyway. So I did all my stuff, my classwork during the day, and at night I got to take all these big 75-pound boxes, lunar orbit pictures, which I would then take to my car And then at night, instead of talking to my wife, I just pour over his photographs. In the process of doing this, I found that there are features that just didn't make sense from what this new paradigm said. I found unusual craters, lava flows, sinuous ruins. Okay, well, some of those are right, but there are other things. There are these small features, these collapse, fractures, and faults that contradicted the consensus view. So I concluded back then that that new paradigm was not the entire story, and that became part of my thesis in 1972. I then took this postdoctoral position at Ames and re-examined models based on actual observations. So I published evidence both in my book and Lunar Morphology in '76, and then started writing papers about this. One of them was about the degradation of features and crater statistics, and I'll share some of that today. That was just inconsistent with the end of volcanism 3.2 billion. We also found out that we proposed that volcanism started much earlier than 3.8, went all the way back to maybe 4 billion years ago. And then we revisited this evidence in 1990 at a workshop. And to my surprise, nobody wanted to listen. They didn't want to hear anything about this. If this was a workshop that was intended to get people excited about the moon, bring up brand new things, and as this workshop was clear, they didn't want to hear about new things. What they really wanted to hear about is what they already believed, and that was going to be the basis for the next mission. Sounds cynical? It is. Anyway, so then we started adding spectrum measurements that I'll get into a little bit later on. One of the things we found was these things. These are small ring domes. These are ring moats. They're kind of like this annulus rounded feature. And sometimes it was a dome, sometimes it was a cone. It looked like mini volcanoes. These are only in certain areas in the area, and some impact mounts. You could see these features there. And you couldn't figure out what these things were, other than the fact that they're preserved. These things have been destroyed. So I saw these in the 60s, and then I started talking about them. And these are the measurements of these, how big they are. They range from anywhere from 200 meters to 400 meters across. But that isn't what the important point is. The important point is that they were way too small to survive. They should have been degraded. Specifically, these moats that are around them only about 40 meters away. That's about 40 yards. That's small in the case of the moon. So let me give an example of one of these features, and I'm going to throw you some pictures so that you know where you are on the moon. This is the crater of Schultz. It's a crater, it's a mare-filled crater over on the western side. It's north of Mare Humoral, north of the crater Gassendi. And one of the things I realized as I was looking at the power photographs later on, I realized there were some strange things. Let me step back. From the lunar orbiter pictures, I actually found these things you can see up in the upper right. And it doesn't not very clear, but if your imagination is good enough, you see these things that look like donuts. Those shouldn't be there. Turns out this is right at the Surveyor Limb landing site. We landed right there. Now, when you look at the statistics, it said it gave you a date, but they didn't land in a place that had these particular features. And this is why I bring up Patron, because when you look very carefully, you can begin to see very clearly these features everywhere. In this case, the sun is coming from over this door here. And realize here, this is 300 meters, and we'll get too close to it. About 300 meters across is a scale bar. This should have been destroyed. And this is what drove me to start mapping them in different places on the moon. One was the crater Latron, where I had many of them clustered. And what I found was that they were distributed all over the moon, something I did not expect to see. This was published in '76, and it was shown the Flamsteed Ring, an area near Meislin, a place over on southeastern Tranquillitas, and a couple of areas up in Imbrium and toward the western edges of volcanoes of the Black. Well, what are they? How do they form? Well, we have several different ideas. One, these represent very thin lava flows that protruded across the surface and surrounded actual volcanic activity. Maybe like a cone and flow, or maybe two different scales or stance of the cone. The other is maybe a tumulus, and tumulus is where it simply bulges up from the flow, so the flow would come around. The other possibility is that it actually collapsed. something collapsed and formed this feature. One of them would be you had a lava flow that came over an old crater and it sagged and cracked. And that cracking continued through time. These were all the things that we suggested as a possibility. Again, to show you this business of how you degrade a crater with time, that's a typical idea. Now, let me show you a crater that should have been completely destroyed. And that's that crater right there. I've got it turned upside down, so now it looks like a dome. If you turn your head upside down, with the sun coming now it's from this side, but this picture is coming from the other side. But it's barely visible. That crater should be gone. It's not. So how? This is where we get into something called crater statistics. I'll give you sort of a short course on this. No tests. I won't ask you again, but you're going to ask me if you want. What we use, without samples or in areas where we don't have samples, the only way we can date a surface is to look at how many times they got hit. Craters of a certain size. So we use that as our clock. And you notice this curve, this is an actual crater curve, where we measure the number of craters in an area as a function of crater diameter. And notice there are two different slopes on this thing. And one, if it comes up, oh yeah, I just wanted anybody not used to log numbers. At the top, that's in meters, all the way from 100 meters. If you imagine 300 meters about par 3 golf, if that doesn't give you any sense. And on the right, it is in terms of number per kilometer squared. So something about 100 meters would have one crater of that size at this age in 1 kilometer square, about larger than 1 kilometer, so larger than 100 meters. So there is a slope, and that slope defines what is called a production slope. In other words, you count everything that you can see because nothing got destroyed. This is a different slope. This is the slope that's called an equilibrium slope. This means that with every crater that's formed, another gets destroyed. So you're sort of in this period of stasis where everything stays the same. In fact, I can show you an example of this. If you look at something that's older, that curve would shift over to the right. If it's younger, it would shift over to the left. But it's more than that. It's not just dating. It turns out that this tells us something about the nature of the surface. We discovered that if it's this hard surface, that equilibrium line goes up. If it's a soft surface, that line goes down. So now we get very complicated if you're not thinking. This wasn't the way people thought back then. It was really just make your slope lines, give me a date. So how old? This is, I'm going to show you one example. This kind of gives you a sense of what this looks like. On a low sun, it looks like a rainy day, you know, in your pond, except frozen in time. So there were some experiments done by my mentor, Don Galt, back in 1970 and 60s, where they repeatedly impacted into a large bucket of sand. It was about the size of, half the size of this room. They got it in a mezzanine and firing down. And they kept on firing with a certain size distribution. And you can tell after you get to about to this point, you can't tell one surface from another. What you're looking at is the equilibrium surface. Your eye tells you nothing's changed. When you look early up, at the top line, the second line, you can tell that more craters are forming. So that's what equilibrium does. And so that's what this really illustrates in a visual way, the crater equilibrium. So surface age doesn't seem to change at all. If you get down to small craters, everything looks the same age. So then how can we use this to well, here's an example of the equilibrium curve. There's the young mare. I can put actual data here for an old mare. And so now you get what is called a transition diameter. And that would be right down there. So that would actually tell you a diameter. Or you can go to this other line for this younger line, and it'll give you a different diameter. So you have two ways. Either you look at the way that curve moves across, or you can look at one number, which is the size of the crater, the size is larger than one given crater in that area that correspond to the map where the equilibrium line meets the production line. Now that's a lot of words, but it works. But this is only relative age. This doesn't tell you anything about absolute age. Unless you know the fluxes, and people spend a lot of time looking at meteors coming through the atmosphere, looking at estimates of particle flux. That was where we need it. You need the data by looking really at the samples. So that we need from rocks. So I'll give you a quick run through. Here's one example. This is the inside of the Atlantic plane. This is the hangar. This is where they landed at Apollo 15. That was 3.3 billion years ago. And you can notice that this transition diameter, 200 meters, 350 meters, they all seem to be about the same. Notice these are all old. So Mars basalts tend to have this transition diameter greater than about 300 meters diameter on this particular type of plot. Ring moats are much smaller than 200 meters, and moats themselves are only 40 meters. There's no way they could survive. So this is consistent with basalt age of around 1 billion years, based on what we discovered back then. But there's something else. What caused this hump? There was a hump. We kept on seeing on this. Turns out there's a really interesting cause for that hump. Most of them occur when there are really young lava flows, about 1 billion years old, which, by the way, was sacrilege back in the 80s. They kept on looking for the samples, they couldn't find them. And recently they've gotten to a site that at least one of the Chinese missions has an age of, I think, around 2 billion. So now we can look at the contrasting erosion rates depending on this regular depth. Now, regular depth is what that surface soil of the moon resulting from the rapid repeated impacts by meteoroids. So there's that our production slope, and this is our production. So all the craters are on the surface, and here's that equilibrium crater where one crater is lost and another crater is formed. And it turns out that we figured out that what we're really seeing is the fact that way over there on A, when you get to that flat line, that's where all those craters are inside the regolith. They're inside, so they degrade very rapidly. It's easier to destroy something in sand than it is in concrete. Anybody who plays in a sandbox know that. I've spent 40 years doing that. I know that. And that was after that's after graduate school too. But as it gets to larger craters, now you're trying to degrade something that is hard rock. That's harder to destroy. So one possibility for the hump is that these are surviving craters. These are craters that are just simply getting away with it because they're harder to destroy. The other way is this could be the result of something added to the flux. Now, what could be added? Well, it turns out these could be contaminated counts. These could be craters and lavas. Is that fictitious? No, not at all. If you've ever been up to Sneaker, or I don't know, you'll see these beautiful lava flows with holes in them. In fact, there are good. In fact, that's the distribution of those craters that you see. That's the size distribution of that whopping lava field. The excess craters are what I plotted out in blue. So there's an excess of craters. The other idea is that it could be something else entirely. It could be contributions from incompletely buried craters on the older unit. In other words, it's just this. So the small craters are destroyed completely. The large craters are still there, but we'll count them anyway. Because we don't know any about it. We can't tell which one's doing what. So that's covered, and that's the excess crater. That's the idea. Now, why is all this important? Well, it gets down to this. We can, if we don't understand that, we can't get a proper age. For example, here's the Aristarchus crater. That crater has been estimated to be about 450 million years old. And that has a diameter of that transition diameter of about 85 meters. 175 meters, excuse me. Now, if you go up into another crater like Dawes crater, and then I go up to, you can see how the crater's transition crater diameter is moving over. And then we look at Copernicus, and Copernicus, we actually gained it 1 billion. And it has a diameter of 160 meters. We'll come back to that number when we take a look at lava flows. So again, compare that with 200 meter for basalt with ring dome moats. So mare areas with ring dome moats seem to have many more, seem to be much younger than Copernicus based on this, but the craters are larger and weaker targets and they also degrade faster, and that affects that equilibrium level. So the correction indicates an age about the same as Copernicus. Well, now I can show you why that's not the case. You can look at this picture. In the upper right are young basalts. These are lavas that invade this rill that's coming in here. That rill is being filled with lava. But if you look closely, you can get a sense of how many craters are on that surface. Which is really bland, right? And yet, if you look up here, in that area, look at all those craters. Which one is older? If you're using crater statistics, the one on the right is older. Can't be older because it's a bang. It's going in between that on the surface. This is from the lunar highlands. That's from the lunar lowlands. So if you don't like the statistics, I can show you a picture. And that picture gives you confidence. Oh yeah, this is right. This is related to how rapidly craters get destroyed depending on the material they're in. So, turns out units with ring moats are going to be underestimated if they're calibrated by counts on weak units, for example, crater ejected. It's okay if you compare it with the same type of target, like another mare basalt. But the actual craters could represent an original surface, but in this case, you're either dealing with additional buried craters to the counts, and that's consistent with these ring moats. But if so, that means that surface must be young. It must be less than 800 million years old. And that, the reaction I got when this was first published in '76, were comments like, unimportant. Just small areas, don't need to worry about this. Or, so now it's been almost eventually forgotten or ignored until 2017. Oops. What's in there? Well, the broad covers by lunar reconnaissance order changed everything. And in 2017, there was a paper published about marine moats that were proclaimed as discovered. There's a brand new discovery made, and it said that these things indicated, and by the way, even though it was a new discovery, but the real point, hundreds of these things, many more than I saw because of lunar orbit. You can see these and all these little yellow dots. These are all clusters of these small little, all these ring moats are there. But they came to the same conclusion.
Peter?
Yeah.
Question?
Yeah.
When you say rediscovered, didn't anyone ever read your original papers?
That's what happens when you have a new mission. That's one of the sublines of this. And you'll see this as you go along. This isn't just once, it's happened several times. It was read, but the implications were not recognized.
Because if they're going to do it, you would think they would look at the research that's come before to formulate.
When you have a mission, you need to find something new. It's a mission period.
Dr. Schultz, in some of those photos, it looks like there are a lot of lunar domes. Could ring moats be collapsed lunar domes and not craters?
Well, they are domes, and some of them collapse in the center. And some of them, but the craters themselves are pretty much, they're either degraded craters or else they've been filled in.
Because they look very smooth. The walls look smooth. And I would think if a dome collapsed, it would be pretty smooth.
Well, true, and that's another possibility. These things are still going on and they're still forming. I'll get back to that in a second. Well, they also came to the same conclusions I had, but they had to be young, but they went beyond that. They said it's as young as 100 million years old. But then in a later paper in 21, they agreed it's about 1 billion years. And in answer to your question, this mystifies me too sometimes, but it's the nature of the beast. But here's what you can use visually. Let me show you that. Number one, it was inconsistent because of the superimposed craters and degraded donuts. It could not be 100 million years. It is consistent with 100 million years. Let me give you an example. Here's the floor of Copernicus. Now that's solid. That'd be like a lava. On the right is Tycho. That's solid. That's 100 million, 800 million, Now let's compare that to Aristarchus. I've got 450, it should be 175 million. And now you put in the size of these moats, these dome moats. They look nothing like that. It doesn't take to tell you, there's no way that that could be an original surface that hasn't been degraded. So that's kind of the end of this whole business. Looks like dome moats don't tell you anything new. It's not active. We don't have the moon ain't dead yet. It's basically we're still dealing with things that are long gone. Wrinkle ridges have been known for a long time. You guys have seen this. If you ever look at movement tells you see these gorgeous wrinkle ridges, especially in Mars Serenitatis, on the edges of Serenitatis. But lunar orbiter, Soda, and Apollo revealed in beautiful detail when you see the lava flow going across and then being modified by those wrinkle ridges. It's most obvious in these basaltic morae. And as a result, some people call them morae ridges. And in this 1970s, they actually thought these things were leftovers from the cooling of the lava. When the lava cooled, they kind of take your hand and go, you're old enough, you can go like this to your hand, you see wrinkles in your hand, right? Well, that's the same idea. If you wrinkle your hand, and that means it's getting wrinkly because the lava is cooling and settling. But then they realized they were tectonic features. Let me show you some examples. There's a problem. Many of these things circle molecular basins, and they have two components. One is this broad arching you see on the right, and the other one is this narrow sinuous ridge. That's all positive. Sometimes your head will play funny games. How many people see these craters as domes? Anybody? Good. All right. When I used to teach, I had problems. The only thing I could do is teach what time the students stand on their head. So the idea was geophysical models were that they had mass downloading, which means there was so much dense lava, it would sag, and then that would cause these wrinkle ridges. The other idea was a cooling and shrinking moon, but then stopped soon after the end of Mare volcanism. Let's take a look at this close up. This is in my book, Mythology. And you notice the scale bar, that's about 3/4 of a mile. You could know about 1/3 of a mile across. And you see what these ridges are actually going inside a crater. It almost looks like a lava flow, right? It's not. These are actual faults that are coming across these pre-existing craters. So this has to be up. In the case on the right, you can actually see that there are boulders that are made, the sharp branches, and you actually see boulders, the rock patches, those are actually boulders that are being exposed through the megalith, through that dusty surface that's created by all the impacts. So in this case, this is not old. The moon is still flexible. So the moon ain't dead when it comes to tectonics. And not just the Mare ridges. In fact, it's kind of funny. Some people use Mare wrinkle ridges to call whatever you saw wrinkle ridges. They would say, if you saw it on Mars, we would say, oh, that means there must be a lava there. Why? Because they used the term Mare ridges. No, we knew even back in the 60s that you could see these wrinkle ridges that go into the highlands. They're often less complex, and it was transitioned into little cliffs like a fault line. And again, they cut across small craters, and they would still must be active, inconsistent with most models. There's one example right there. In the highlands. Well, and this was again pretty much ignored. In fact, according to one reference back in 2010, their global spatial distribution was unknown. Here's a good example where you see the wrinkle ridge in the Mare, and then it keeps on going as you cross. This is right out of my book. And then the road becomes this formula. And it's solid stuff that we couldn't see. We can actually see the smaller size features if you look at the infrared. You know, if you're flying over hunting for somebody hiding in the woods, if it's in the infrared camera on your drone, you can see them as spots of red. In the same way, in the case, even though you may not be able to resolve it, you can see the thermal signature in nighttime. Now the diviner instrument on the lunar accelerometer. And these were hotspots. Not just flat surfaces, not on slopes, but also on flat surfaces. So these were places where the regoliths were moved. So we interpreted, this is with a student, who was then at that time a student, Adam Valentinas, and I suggested this was the area where the regolith was actually draining as everything flexed up like that. It caused cracks, and the regolith simply drained back down into the void. Not just around the Moscows either. If this was only related to the sagging, you would think that you would see them only inside these big basins. It's not. It's much broader in distribution, and some of the hottest ones are in this area here. In fact, we call this neotectonics, because you just can't do that. This means that, in fact, it was probably active and was new. Well, brand new equipment, incredibly high resolution, broad coverage, and now they found over 3,200. In the first paper, they found 14. I found 7 in my book. And that was worthy of an article in Science. Now, 3,200 discovered. And these are now interpreted as global thrust faults. And they even recognize as tiny gravity. That's also not new. This is from my book where we saw the same type of cracks in a mare. But what's really interesting about this paper, now they're suggesting one way to do this in terms of the orientation of all these ridges in the highlands, these faults, is it's a combination of global contraction still going on, which is against the model, combined with over recession and diurnal tides. So in this case, the moon ain't dead. So far, here's what we got. Volcanism, much younger than many had believed, from 1970 to 2000. Widespread volcanic flows extended to only 800 million years. No evidence of large volcanic flows extending much younger. Clear evidence that the moon is still tectonically active. Ongoing thrust faults throughout the mare and highlands. Local areas of extension. So the moon is still creaking. Now, you can freak and be dead, I guess, but this is not. But wait. There's more. One of the things I also observed when I was doing my thesis, I found these really isolated rough spots in certain areas. And this was, and I'll give you an example of it. Inside the highlands, if you know where highlands is, it'll be coming up in 2 days, I think, on the moon, permanent. It's the intersection of 2 rills. And right in the center is a caldera, what appears to be a volcanic collapse crater. And if you look closely, whoops, let me go back. Look closely, you see these strange features that appear on the edges of craters and also in patches on the floor. But these have very limited covers. I saw them in 4 places in highlands, near the Irregular crater, which I'll show right here. And if you look really closely, that's what it looks like. Another one is in Mare Pequeñas. Another one is in the Harbinger Mountains, western edge of India. So this doesn't make sense either with crater degradation. So the initial interpretations were it was a volcanic caldera, and that's all these are. Well, that doesn't make sense. That doesn't make sense in terms of reservation. The sharp features of topography are just completely inconsistent. So it must be an ongoing process of some kind. And that's when we get to the island structure. And this is when I gave a talk back in 2017. This was a forgotten feature for a long time. It's identical to those features I just showed you. And I tried to emphasize the significance twice, I guess. I did this in meetings from 1970s to 80s. And then things changed in 1990s. When I say meetings in 1970s, like I said, there was this meeting specifically trying to define what was new about it. I presented this result. And it just went kind of like, I don't understand. Most of them were people who did petrology, not necessarily looking at features. So things changed in the 1990s. One was the Clementine mission. The other was Lunar Prospector and Smart 1. Now, if you look at this feature, it was time that I decided to reignite interest, and that came out in a Nature paper in 2006. Again, let me show you again. look at this feature and what's going on. These are looked to be passes of mare in between which are these rough, bright patches. So what are these bright patches? Well, it turns out this whole thing was attributed way back then as the volcanic caldera. It looks like it's on top of a mountain. You can barely, I think, Bob, you tried to see this. You can barely see it with a telescope. It's, if you know where to look on a really clear night, you can see it. And it's near also the intersection of several fractures. What we did, so climate time missing data were available. I used data that was done by State and Pierce, and they were co-authored on this paper. We said, well, let's take a look at the spectrum. Turns out there are several ways of measuring age of the moon. Crater counting, absolute age by dating rocks. The other one is how the albedo, the crater rays disappear. There's another way to look at it, and it's the spectrum. There's a space weathering, and changing the spectrum. And you can do this by doing a spectral ratio. For those of you who care, there's 1,000 nanometer over 750 nanometer band as a function of albedo or reflectance of 750 nanometers. And so when you have a change in composition, it moves off to the right. If you want to look at from fresh to old, it goes up in that direction. That means it's weathered. So can we link these with these features of INA from the Clementine mission superimposed on the Apollo photograph? Well, that area here corresponds to that area around INA. It was also called D Caldera. This area right there corresponds to this crater. So it's intermediate age. Certainly not 3 billion years. We know that surface on the outside is around 3 billion or more, 3.5 billion years old. Okay. Well, what about the stuff down here? What is that? That's INA. In fact, from what we can tell, the floor of INA spectrally looks like it's on the slope of the crater wall. If that fresh, there's no way this has been degraded. How does that happen? Well, several things happen. Again, this is where they're thinking. So let me review this, I'll come back to that. So just review, extremely low crater density, reserved low rate. These things are probably about the height of this room. These are cliffs that surround these patches of these light colored patches. Freshly, speckling fresh, thermally bland, except some cases they're very hot in nighttime. So we suggested as a result, the only thing that we could think of, it was had to be the result of recent gas release. I was not ready to go out and say this is the result of volcanoes on the moon. That it was volcanically active. But I could believe it still could be gas release. What it would do is following these little pathways within this old caldera and just poof. So it would come up and just poof sometimes. Continuous but sporadic. And it would freshen. It would throw away that regolith, which is an old regolith, it's already been weathered, and throw it out and deposit around the structure. But it means it's young, but the structure still is old. So how is this possible? Why? Now, if you use a telescope, you will see this. Highlands is right down here. Highlands is there. It turns out when you look behind these rills, some of them, these cracks, they don't care about the embryo base, they cut right through it. So I've remapped this into a position where I'm looking down, and it's very difficult to see the differences in color. I'll try to explain this to you. But this forms this, when you look down from above, just to the southwest of the embryo crater, you'll see that there's a pattern. There are the regular ridges over here, those are the black. Over here are sinuous rills. I'm pointing this one out because here are some sinuous rills. I mean, here are some ridges that they say must be compression. Well, here, there are also volcanic vents. You don't have volcanic vents when you have compression. You have volcanic vents when they split apart and lava get up. And over here are the gravity, these are the cracks. There's a system on the moon that looks like it has this concentric and radial ridges and concentric and radial gravity. So let's see if we can make some sense out of this. In fact, I mapped this up just for reference. That's the in-rim basin. And when you look at all the orientations, they end up pointing to a spot, not on the in-rim, but an area southwest of in-rim. Now, this turns out to be a really important place because this is also the place that has the most radioactivity. Thorium area is very high in that area. That's only one point. So what did we find out from reconnaissance orbiter? They found tons of these things. Much higher resolution again, much broader covers. Now they're finding them everywhere. And Phil Stuck first did this. It was kind of like a big eye-opener for everybody. And then Brandon et al. In 2014 wrote a very detailed discovery paper about all these different types. And they're all clustered in certain areas. So now they're brand new hypotheses. One said, it's the mare, not the stuff in between. So they proclaimed those patches of mare that you can see. They said those are lava flows. Now, to me, I thought that was crazy talk. Here I am, the heretic. I'm calling him a heretic. Well, the reason for that is actually I can argue that based on the crater statistics and the fact that it's eating into the mare. These patches are eating into them. The other was I suggested that there were forming lavas, and the other suggestion is the drainage features. The idea that they were being pushed by anything was again considered, I think, two seventies, I guess. Well, there is an emission going to this place, called island, called Dimple. And the idea is that they want to be able to land on deep samples in two different places and establish whether or not those mare patches are young or old. And then they're going to go down the rock place and see whether they're young or old. If it's a forming lava, it could be old, but it won't resolve how these things formed still. So that won't resolve, this mission will not resolve the way it's defined, it will not resolve the answer to the question. I just wanted to show you this to see what this is the floor of highlands from the lunar reconnaissance program. They were talking about those flat floor areas being lava flows, which makes no sense. But I wanted to show you this because the extraordinary detail you get from lunar reconnaissance program, and you can see how when people started finding these things, they became enamored with it, just like I was back in the 60s. Now, this is a plot of all those places where they now find them. Up there is highlands, up there is island. We begin to see something interesting. Let's go back to this plot. Okay, went through that, Then that. Oh, this is the point I want to make. What conformed this? And this is when we get back to one of the pieces of research I was doing about what happens if you have a giant impact. The idea behind this feature had been that there's a giant impact on the near side of the moon. It just carved out much of the crust, allowed volcanism to come up on the near side. That's what happened. But there was only one big impact on the moon that we know of right now. And that's the South Pole Reagan Basin on the far side. Giant, 2,500 kilometers across. That's bigger than the radius. So now you're looking at what happens if that could, and this happened when I was doing a TV program, and they asked if they could look inside an asteroid getting hit. So I thought, why not? So I set up a transparent sphere about this big, and I slammed in at an oblique impact angle. And I watched what happened at very high speed. This is about 500,000 frames per second. That was the shock wave that's gone through, and now you're seeing cracking. You notice it's not on the opposite side. I mean, if this was the opposite side of this feature, but now what happens? That's vapor going across. So now that is the final crater. You notice that the antibodal spot, the opposite side spot, is not opposite the crater. It's actually opposite that first point of contact. That makes sense because that's where the shock wave is generated. All the rest of gravity, if the rest of the projectile fails and continues to impact the surface. Well, that was the idea. And that's what it looks like if you take a picture of it. I actually did a little exhibit of high impact art using these things. I think it'd be a great art exhibit. So this is not just looking at the idea that you have this surface fracturing near the surface, and then you have the opposite side. This actually became a PhD thesis of one of my students. We did a beautiful work on this and studied shear created by this and explained the bands around the equatorial band of Vesta. And argued that that's what was happening by shear. By the way, the disruption occurs inside, then migrates out to the back end. So why is all this interesting? Well, let me show you something else we did there. One of my other students, an old ex-student, one of my early students, is a computer guru. So he did some computer modeling. And he said, well, what happens if we hit the moon really hard, oblique? In fact, a projectile that size should have disrupted the moon, but because it was oblique, most of the projectile just went away. It continued to go. But what it did do was to create this enormous amount of damage on the opposite side. And that line, the dashed line, dark dashed line inside there, that's a depth of 800 kilometers deep below the surface. That will become important later. The picture shows what's opposite in black was the opposite to the South Polacan Basin, and then the white one is opposite for the first point of impact. So here we go again. Embryo, I guess. Now I'm going to try to start putting this into some new context. Arago, I'm putting up these IMPs. By the way, they call them irregular mare patches. Just like the mare ridges, people think, okay, irregular mare patches, everything has to be irregular mare. No, it's nothing. They should be calling these things irregular disruption zones or something, but nothing like mare patches. But again, things get stuck in literature. These are things that I discovered when I was doing my thesis. So I found at least 4 of them, not 3,200. And that's I know. Now, why am I telling you this? Because when you plot up, and this is not, these dots, red dots represent the new ones from lunar reconstruction, but not all of them, they're too small. So I clumped them wherever there are clumps. And you know something? They seem to be occurring along that same set of fractures from Ina and highlands. It turns out that I can also talk about the ring moats and dome moats. And the ring moats and dome moats are now in these new circles. I can go one step farther. The lunar prospector had a detector, a sniffer, alpha spectrometer that actually measured gas coming off the moon. Polonium-210 is 138-day lifetime, and which means that if you see it, it means it's been around for 138 days. But these things will migrate. But actually, these are all the places they found them. They even went to radon, which has a 3.8-day half-life, which means if you're seeing this, it happened yesterday. This was another thing that was completely ignored in the 70s. I knew the guy who first said this back in the 70s from Apollo. And it was really odd. It was really strange to see this guy get hammered. But it was all because of this business about lunar trends of the mountain. You can't have gas coming off the moon. In fact, I knew somebody was fired in Nancy Johnson because that person was mapping out all these locations where amateurs had identified them. How do you make sense of this? Here's one way I'm gonna make sense. This is the moon. That oval right there corresponds to the area. It's not a circle, it's an oval. Roughly perpendicular to the line of the axis of what we think is the impact trajectory. That's the damage zone based on the models at a depth of about 900 kilometers deep. So now what I want to do is let's get crazy. Let's plot up all these features of the IMPs. Now we'll start putting on all those things. And you begin to see that there is a common thread with all this stuff that's going on seems to be localized around. If it's a big giant impact basement occurred on the near side, okay. But some reason this is still being reactivated on here has nothing to do with the environment, nothing to do with anything else. And I will also point out that if you're looking at all the seismic, somebody did a seismic study looking at the depth where the seismic record is coming from. It's all around 900 kilometer depth. These are where all of these seismic sources have been backed out. Coincidence? I don't know now. But I tell you what, if I were in charge of the program, I would have a sniffer, something that would detect gases going on and off at different places at different times, and I would have a seismometer on the moon. So the moon ain't dead. Even though it likely ended between 500 million years ago and 1 billion years, left behind these ring domes and moats. They were later also controlled collapse pits, a lot of collapse pits, which found the lunar order. Still flexing, forming the thrust faults, reactivating some ancient faults related to the South Volcanic basins. But I would suggest there's still gas being released. Unlikely from the regolith. A study was done back in the 70s saying it could not come from the regolith. That the diffusion time was not appropriate, it couldn't do it. So I'm suggesting these are still related to these reactivated faults related to these deep things. So if you can have thrust faults going on, you can also have these other types of faults. So the moon ain't dead. It's alive, but just barely. Thank you. Happy to answer any questions.
What percentage of the moon's molten core, how does it compare to Earth's? Because if
So
you,
multiple is very small. It's, I think the range is 200 kilometers or something like that. It's very small, but these moonquakes are coming from depth, and they indicate most of the moonquakes are coming from areas that are shearways where they go through them, go slower, and so it's kind of like it's not completely hot, but a cold year. So it's interesting that these things are localized. When they turned off the seismometer from Apollo in the 70s, because it cost too much time, too much money to receive them in the radio telescope, we would have these records. And if you have more seismometers, we would be able to solve this stuff, by the way. By the way, one of the things I'm trying to is something that, we can see if I know as much as I'm going to ask myself. Okay, let's go like that. Okay, you see this? Could you see the puffing? The only people who get to see this are amateur astronomers. I'm convinced that with how excessive amateurs are, that if you set a narrow band pass filter of something in sodium line and looked at places where Ida is, now you know where all these other places are. I have a feeling that if you have them so just beyond the terminator, so that you have it dark and you can block off where it's bright, you might be able to see the sodium line. Why do I say sodium? We know the moon has a sodium atmosphere coming from bombardment from the sun. It's trapped in the regolith. If the regolith gets tossed up, it will also toss up any trapped sodium. So my suspicion is that you might be able to see it, but you have to look. Nobody's gonna look, except for the amateurs, I swear. I mean, just like they didn't look, they didn't think about ring moats, they didn't think about these crazy IMPs. When did they look at them? Not until they had a brand new mission. Of course, it's a whole new story because of all the detail. But leaves the same questions. Yeah,
What the frequency in the feeders?
well, it's the sodium D line. I forgot what it is. Everyone know that? You know, the sodium D line that's why I have to be careful having it on the backside because the sun has very strong bands. You can even look at it and get very sensitive, so you might even see the fill in the sodium line. You can find that online very easily. Sodium D line. Yeah,
So sodium becomes gaseous.
yeah, this is not, it's not
Because of
salt.
the pressure.
Yeah, it's all these are atoms. This is sodium atoms. So they're getting released. And so I'm sure that it's possible. The other is just looking, but now with digital stuff, you have to do it so you can record it and have a record. Remember, they said, one of my colleagues claimed you could not have an impact flash on the moon. He got up and said this at conferences. And yet, you could see the impact flashes. All these amateur observations of impact flashes on the moon were real. But unless you recorded them, you couldn't prove it to anybody. So they had a whole program at NASA Marshall recording these flashes. And it's only on the dark time. And you only see a portion of it. But they're flat. I think some people suggested having an orbiting spacecraft to try to measure flashes on the moon as a way to say what the flux rate is. That would be important for any future landing site. Why? I keep asking my questions. It's because if you're on the moon, the threat is not from that one impact. The threat is from the ejecta. Why ejecta? These impacts are coming in, they're going to hit at speed, 10, 15, 20 kilometers per second, maybe higher. The likelihood of getting hit directly by that is pretty low. The likely to be hit on the ejecta is much higher. And guess what speed that is? That's the speed of a bullet. And rather than busting up and being destroyed by a thin sheet of paper or a thin sheet of anything mild you have on you, it penetrates. So that's one of the reasons why I think they need to have a program that gets a very good idea of the flux, and especially the size frequency, because I think it's a real hazard to be able to move for a long time.
If the core of the moon is, the molten core is approximately 250 kilometers, does that mean that there's fractures that go from the surface all the way to the core for that
No.
gassing to happen?
No, that's why I showed you that. I think the gases are coming up through these cracks, because just because it's there doesn't mean you can't know how the gases are released. And so I think you can still beat death. There are places even on the Earth, dye streams, is where you get the diamonds in Arkansas. These massive explosions of gas coming in. Those are hot volcanoes, but they're driven by hot gases. So the question is whether or not these will be hot. I think the cold gas, that's why I don't think they're violent. That's why I don't think you have cones around them. I think they come up and they just have enough energy to blow them off. And if you look at islands and other places, you'll see that the places that are pretty trash, other areas that get covered up. Some of them you can't even see them full of red, other places you can. So that's my interpretation. Yeah.
If there's all this activity that's previously unaccounted for, would that change the way that we consider the rate of crater degradation?
I don't think it could. For example, if I'm wrong, that these features are 3 billion years ago, which doesn't make sense with crater structures, just tell you like that. But if they were 3 billion years ago, then the degradation models are wrong. In fact, that's part of my paper I put in. I showed how ridiculous a little dome like this, if you use a degradation model, the dome like this would end up looking like that. Impossible. That's why I was so convinced this was wrong. The degradation models were wrong, or this had to be the answer.
We have a question online. Go ahead, Greg.
Yes, Dr. Schultz. Have the Apollo moon rocks that have been returned, have they been accurately dated using radioactive isotopes, or have they all decayed away?
No, they haven't decayed away. That's why we get these dates. They come from the decay, and actually also from, both the variety of methods they use. Uranium, lead, various methods they use to date these things.
Oh, okay. So
Yeah.
that's how we know the age of
Yeah,
the mare, the lava as opposed to the
right.
highlands, the lowlands, the feldspar. Oh, okay, good.
Yeah, but only in those areas where they landed.
Oh, yeah, where we landed,
Now,
right.
maybe they'll find a rock thrown in somewhere, but then they kind of look weird. But that's how they determine, in some places, they have some rocks as old as 4.35 billion. It must have gotten there from someplace. It was tossed out probably by another crater.
Okay, thank you.
I have shown people the little shield volcanoes there,
Hortensius? Yeah.
with a telescope here, but I'm not quite sure how old those are, and there's any suspicion of any still ongoing activity.
Hortensius domes are the shallow domes. These are shield volcanoes, kind of like Hawaii.
Yeah.
And there are many of them clustered. This is on the southwest side of England. I believe this new study has found some more of these patches in that area. Those domes will date back to 3 billion years, at least 3.2 billion. But then the question is there anything else going on over there? This is why I'm kind of excited to see all these patches now. Because it says you have many, before I thought, well, you're gonna have to be really lucky to see it in highlands or see it in Arago you're not gonna see it. Because that could be a drainage thing. This is what they thought was a possibility. But some of those other locations, we'll be spending a lot of nights. Now is a chance with all these different locations that are clustered. If there really is something coming off of them, or if there's any activity at all, you have a shot. I've gone back and other people have gone back and chained and compared what it looked like a little earlier or what it looks like today. You don't see any change. However, that doesn't answer the question. I know that, like in the case of Ina, there are places that are very, what I call it, rocky, exposed, and in spectrum, there's some very strong olivine bands. It's fresh, not degraded at all. I think those things have been freshly exposed. That's areas where it's been knocked down. The center of the island is darker. I don't know if you noticed that, but the center of the island is darker. And I have a feeling that's where stuff came back, went out to the outside or the inside. So I think it's still going on, but it's going to be not every day, not every week. But darn, if it isn't worth a shot, you know.
Yeah.
But it's going to have to be recorded. That's why it's going to be able to fix anybody, unless they have stuff.
You got more people on the bandwagon, more researchers?
But yeah, I think now I'm just sitting aside and watching what happens. I mean, what they're doing is very constitutional. These new studies are just really great. But just so you guys know, you've had a lot of my students give talks here. You probably don't know, I think 5 of those students were the ones responsible for dark vision. So some of those students, I bet you, look up these students, they probably gave talks here and they were very much involved and responsible.
Thank you for mentoring.